So I started the recording. Okay, this is the last last class for this semester. Okay, quick review. Just 1 second. Most likely my screen is extended now. That's why you're not seeing what is happening here. I know the way around. So I gotta do right click, display setting, to duplicate, keep change. Should be seeing it now here. All right. Excuse me, sorry. So this is the last class. Okay, everybody please pay attention. So a few things first. First thing first is the exam, right? There won't be any physical exam. It is online, the last one, as I announced. It will be available for you today, and it's due on the day of the exam day. Okay, I believe the exam day is Tuesday, so it's due on Tuesday. All right, so any question about the exam? I did talk about the exam in last class as well. It's 50 points, right? All other exams are 100 points. This is 50 points because you are not doing in class. Okay, you're just doing take home, and you had so many exams already, and I didn't quite cover that much. I don't want to do comprehensive. Okay, whatever I covered from last exam is here. So whatever I covered, okay, what I covered the internal flow. Remember in last class I started with the internal flow. Okay, the questions is from internal flow, except you'll be getting some subjective or theory question, okay, which are not that in-depth question. It's just one line answer I want from radiation. So our agenda, now it comes to agenda for today's class. Our agenda for today's class is to finish the problem for internal flow. One problem, the last problem we did, right? One problem we're gonna do extensive one, another one we did in last class, and I'll talk a little bit about the radiation. Okay, so those are two agendas. So without further ado, let me start because the time is running. Okay, everyone, please pay attention. Get your pen and paper ready because we'll be doing a math, which is from internal flow. And if time allows, at the end of the class, I'm gonna quickly show you the exam as well. Okay. All right. So please be attentive so I can reach my goal without any issue. So the recording started. Obviously, those who are not here, hopefully they're gonna watch it. So here's the problem. Let's start reading through the problem. Don't get confused with this problem with the external flow problem that we did in class. A house is a house problem, but this time we are talking about the ducting. Okay, what happened in the ducting? Duct is internal flow. The air, hot air, cold air, whatever you have, depending on the season, flow through that. And you may want to know how much of the heat transfer happening from the duct, right? So how are we going to deal with this kind of problem? So let's see what the problem says. The problem says this way: a hot air at atmospheric pressure and 85 degrees Celsius enters 10-meter long uninsulated square duct. So you see, on one statement they have so many keywords. Like uninsulated means there is no insulation on the duct, means we are constantly losing or gaining heat from the duct. Now, why do they do that? Why do people put uninsulated duct? You have seen the duct in house, in the attic before, or in crawl space. Did you see any insulation? Oftentimes you see, oftentimes you don't see, right? So depending on the zone you are installing that. Why you want to put an uninsulated duct? Anyone? Any idea? Okay. How many of you walked through the HVAC lab? Did you see the ducts are insulated or not insulated? It was not insulated. Why? Why do you think that? Because it's in the conditioned space. You don't need insulation. You won't be losing, right, mate? You won't be losing too much of heat. You won't be getting too much of heat, right? But what if you are running that in an unconditioned space? What could be the unconditioned space in your house? In the attic or in the crawl space? Then if you wanna keep it this way, like uninsulated, what is the problem? You will be bleeding money, right? In this bad, you don't want to do that. You definitely want to invest the insulation, right? When it's running on those places, as long as those places places are not properly, warmed or conditioned or cooled or properly conditioned, depending on the season. Anyway, now moving on. So this says here 85 degrees. So 85 degrees Celsius, air is moving, and this volumetric flow rate is given. So that's what is here. So a square duct that you can see already, okay, and it's running in the attic space. Okay, so you would be assuming like the attic temperature is very close to house temperature. You don't want to spend too much money on the insulation. Have you guys ever involved with the insulation in your house, like modifying insulation ever? Renovation or the new house? If you're gonna go to Lowe's or Home Depot or a box store, you'd be seeing how much it costs. It's very expensive nowadays, okay? After especially COVID, you may want to save the money. Now, all I'm saying, in attic, if it's conditioned, you may have to do the math and figure it out whether you're gonna go insulation or uninsulation duct. All right, what else they gave you here? So they gave you the cross section of the duct itself, and they gave you the volumetric flow rate, 0.1 meter cube per second. The duct is observed to be nearly isothermal at 30 degrees Celsius. Now, this isothermal is a key word. What does isothermal mean? Same temperature, right? It means the duct temperature everywhere is 70 degrees Celsius, right? So determine the exit temperature of the air and the rate of heat loss of the duct, and evaluate the air property at bulk mean temperature 75 degrees Celsius. So then the final question is it a good assumption that the bulk temperature is 75? Okay, now so many things happen here. First of all, they are asking what? The exit temperature of the duct. Why do you care about the exit temperature of the duct? The entering temperature is 85, right? Why do you care about the exit temperature of the duct? That one is a little tricky to understand, right? Because the exit temperature of the duct tells you what? How much of the heat that you are losing on that space. Maybe that duct is running to another space where you'd like to get conditioned, right? Does it make sense? So if 75 is the exit temperature you found, that could be not sufficient for the next place that you'd like to warm up or cool down. Does it make sense? Did you got it? What I'm trying to say? Okay, the second point is asking you how much of the heat that you're losing in attic. Why do you think this is important? The heat, we are talking about winter, right? The heat that you're losing in attic, does it have any benefit to you? Indirectly, a little bit, partially, but mostly it's gone away, right? Why partially? You understand possibly that attic would be warm, would be losing less heat from the uninsulated duct. But our main goal is not to warm up the attic, right? Who wants to warm up the attic? How many times you go to attic? No, right? In 5 years, maybe 2-3 times, right? Maximum. So basically, your goal is to reduce the amount of heat loss as much as possible. Now, while you are doing this math, like this kind of math is going to tell you when you are designing whether you have to spend money for the insulation or not. If you're seeing too much of the heat loss that you are losing, you're bleeding too much on the attic, right? That is a big red sign, right? You know what I'm saying? So like the capacity of the whatever furnace or whatever you are using to warm up for the year, right? And the capacity of that furnace is say like 2 tons, tons, right? Usually they don't say by tons for the heating, they say like BTUH, right? But it's the same thing, 1 ton equal to 12,000 BTUH, right? Say like I'm saying 210, easy to understand, but or 36K, right? Or 24K, 24K is 2 tons, 24K BTUH. So see, if your capacity is 24K and you are losing 1K in attic, what do you want to do? You want to go buy some insulation, right? Does it make sense? We're feeling excited now with this problem? Why this problem is important? Alright. If you got it? Alright, so let's start. Now is all the technical glitch and everything, okay? It's the boring stuff is going to start to come. So let's start with the givens. What are the givens? So the volumetric flow rate. Everybody remember the volumetric flow rate V dot that we use, right? So that value is given as 0.1 meter cube per second, right? So then they said it's a square duct, right? Everybody's taking class note. I'm not seeing it. So it's a square duct, right? So what square duct means what? Like the one length is 0.15 meter, right? And the length of the duct is 10 meter. Ti, the inlet temperature is 85 degrees Celsius. Ts, the surface temperature is 70 degrees Celsius. Okay, and you want to draw a sketch, right? What is that sketch should look like? Sketch should look like the similar thing like the square duct that you're seeing in the question, right? And then you have this length here. What is this length? L. You have this Ti, air temperature entering, right? You are putting the symbols for what reason? So you can point it out on the given parameter, right? You don't want to put the number in the sketch. Always remember that you would like to put the symbols on the sketch. All right, what else? The surface temperature Ts, the exit temperature Te, right? That's what you need to find. What else you need to find? Amount of heat loss, Q, that is happening here, right? You got it? So these are the things that you are interested. And they said this is square duct with a length is A. So for square, you guys remember how to find the cross-sectional area, right? It's the same size, right? Length and width. So A square would be the surface area. How about that? So like the surface area, let's see if you understand it. Okay. What kind of surface area you are interested? Assume this is the duct. Everybody seeing that? So air is flowing to that. So air, if air is flowing to that, they gave you what? This one side length, right? So you can find this cross-sectional area. But do you want to use this cross-sectional area for the math? Are we losing heat in this cross-section? We are losing it where? In this side, right? Everybody see that? So what is this side cross-sectional area? Not cross-sectional area, this side surface area. Which would be perimeter multiplied the length. Everybody remember that? So it would be what? 4A multiplied by the length, right? Everybody got it? Alright, perfect. So let me write it here. The surface area since this is not directly given, I'm writing it in different ink, black. So PL. Now P is the perimeter. You guys remember from your elementary class, which would be 4A, right? I was talking about that, right? That's the perimeter multiplied the length. All right, now you can do the math to find that. We're going to do it shortly, but let's move on with the problem itself. So what we are trying to find here, two things, obviously. The exit temperature. Now, first time I'm writing TE, so let me write it here. What is that? Is the exit temperature. You may write Ti as the inlet temperature as well, but I'm skipping that. And amount of heat loss, right? Amount of heat loss. So which would be Q from the duct to the attic space. I don't want to go any further. I do understand what I meant by that. So a few more things like the properties. You see, I don't like to write everything one after another. That way you won't be seeing the whole picture. And just want to write side by side. Properties, let me know if it confuses you. So on the properties, one thing they give you, everybody remember the mean temperature for internal flow? That's the emphasize on last class. Everybody remember the film temperature? Film temperature? When do you use the film temperature? For external flow, right? The mean temperature you use for internal flow because you in external flow you don't wanna go with the free steam temperature and the surface temperature because the free steam now goes with the complex dynamics as a mean temperature inside the conduit, right? The conduit could be square, circular, triangular, hexagonal, whatever way you wanna go conduit, right? So anyway, the mean temperature they gave you 75 as a starting point. Now, the mean temperature, you don't find it that way, right? You usually do the average. Now, the surface temperature here, they say 75, right? The exit temperature, do you know that? That's what you're trying to find. What did you do in last class, Isaac, to find the mean temperature? You did the average of inlet and outlet temperature, right? Is the outlet temperature known? No. That's what we're trying to find. So the mean temperature that they gave you is based on assumption. So when you're going to find the exit temperature, ideally, you should be finding the mean temperature then and redo the math. Right? Everybody understand? It's so tricky to understand this point that I'm trying to establish. So anyway, the mean temperature they gave you, assume Tm is 75 degrees Celsius, right? And the Prandtl number, the mu, the dynamic viscosity, the rho, the density, the Cp, the K, specific heat at constant pressure, K is the conductivity. All those properties we're going to find at that temperature for what? For air, because the air is flowing, right? Now, these properties that I wrote over there, right? What are those properties called? What is the term that they use? Thermophysical property. Thank you. Thermophysical property. Remember that. So if you're going to go through the table, where are you going to find these properties, by the way? Appendix, right? You have seen it already. Either book, in Cropper or Sanjel, doesn't matter. Go through the appendix, look for air temperature 75 and find all the properties. And this properties value you'll be finding. The Prandtl number is 0.7166. The mu, the dynamic viscosity. Is there any other kind of viscosity you guys know? Kinematic viscosity, which is nu, which is mu over rho. Rho is the density. Anyway, so the rho or density is 1.015 kg per meter cube. Cp is 1007.5 joule per kg Kelvin. K is 0.02917 watt per meter Kelvin, right? So you have this mass flow rate. So mass flow rate. Okay, m dot. Now this equation from fluid mechanics, you did learn about this equation, right? You may write it this way mostly, right? Everybody remember the rho AV? I emphasized this in last class, right? But rho AV, that AV is the volumetric flow rate. How many of you remember from fluid class? That A is the cross-sectional area, V is the velocity. Now the other V dot that I have is not that velocity. What is that? They call volumetric flow rate. Because of the dot is per unit time. That's the rate. Everybody understand so far? All right, very good. So these are the equation we need to use them. Shortly we're going to use it. Now we've got to do some assumptions. Let's see how many assumptions that you can come up with. Okay, I'd like to start with assumptions. Any assumptions that you can think of? Anything? Steady state, the first assumption. Anything else? How about this one? The Reynolds number critical, it could be 2300, 3000 depending on the book, right? That's assumptions. So you'd like to make it. Steve, you said another one. Which one it is? Thank you. Constant properties is another. Now, you may argue here. Okay, why do you saying it's constant properties? Because I'm getting the properties at a temperature which I'm assuming is the correct mean temperature. So I should be getting it right. Now, here's the thing you have to understand: the properties of air won't be constant from the inlet to the outlet of the tank, right? It is changing wildly within a range, though, not means like too much, but still the changes are there. That's why you got to do this assumption: constant properties. Any other properties? Any other assumptions that you'd like to make? How about radiation? Are you accounting radiation in this problem? No, because the temperature difference. You have to understand why you are not accounting. Radiation could be important part in play in this problem, but here it's not, because we are dealing with what? This small temperature difference. Okay, small temperature difference. Radiation has minimum effect. You guys know why? Because you guys remember the Stephen Boltzmann constant value. What is that value? 5.675 10 to the power minus 8 watt per meter square Kelvin to the power 4. You see that minus 8 10 to the power minus 8 means what? It's a very small number. So if you don't have a significant temperature difference in terms of temperature to the power 4, temperature to the power 4, if you don't have that, it will not going to give you that much of value on radiation. Does it make sense? So it's a negligible radiation. All right. I'm talking a little bit too much intentionally, Joe. So this is the only one problem I'm going to do today, right? And I'd like to go like as much as I can with full depth. Okay, solution. How are we going to solve this problem? Any idea? Any strategy that you'd like to make? Anyone? We have the Prandtl number. Okay. If we know that the flow is laminar, then we can use the laminar equation to find the Nusselt number. What you can do with the Nusselt number? We can find the value of the H. What you can do with the H? We can find the value of the Q, right? The amount of the clock. So you see the strategy, everybody understand what I'm trying to say? So what are you going to do first? Find the Reynolds number. If you find the Reynolds number is more than 2300, then you know it's turbulent flow. You'll be looking for the turbulent equation. As you remember, I did show all the equations last class, turbulent equation, right? All right, so that's one way of dealing with that. Now, in last class, if you guys remember, I was showing you the entrance zone effect, the fully developed effect, those things, right? Now, in this talk itself, right, what is happening? If the air comes from the entering zone here, that whatever we're seeing, that means there is an entrance zone effect as well. But that could be your assumptions. You are not assuming there is an entrance zone effect. Why? Because most likely, by the time the air is coming to the attic from the furnace, the entrance zone effect goes away. So we'll be dealing with the fully developed flow. Does that make sense? So that's your basis for these assumptions, okay? And then once it's fully developed flow, once you know it's say like I'm giving you the answer. It's a turbulent flow. Once you know it's turbulent flow, fully developed flow, everybody see that, right? Did you get the Nusselt number equation? Once you have it, then you find the H, then you find the Q. Okay? That's one part of the problem. The other part of the problem, the new sets of equation I'm going to show. So that part of the problem is different, but this one you can deal with these by yourself, right? So everybody, you guys are ready to find the Reynolds number first, right? Try to find the Reynolds number by yourself and see if it's more than 2300 or 3000. Okay, I'll be doing the same thing here, but you try to focus your way. Okay, so as I'm saying, like the Reynolds number is our first goal. So the Reynolds number would be 4m dot p mu. Now p is the perimeter here, and this equation I did talk about it in last class as well. In this problem, the P would be what? 4A, right? And this M is the mass flow rate. And you can find the mass flow rate by the way, there is a dot you need to put on the top of the M, right? To find the mass flow rate. Okay, so by using this equation, rho V dot, right? As you go with me so far? Perfect. All right, so now that you have all the equations for Reynolds number, you're going to start to plug the parameters first, okay? And then you'd be start to plug the values, which I'll be doing it here. So you have this 4. What is the value of, okay, this 4 and 4 can be cancelled out. So I don't have to worry about this 4. So I have this 0.15 meter, that's one side of the square duct, and I have this 2.075 10 to the power minus 5 Newton per meter second. By the way, this value you found it from the table, right? And I have this 1.01 kg per meter cube, and I have this 0.1 meter cube per second. That's the volumetric flow rate. And once I have everything, I'm gonna find, look at here, how big is the value? Is it too much compared to the critical number, right? Harley, what's the critical number? Reynolds number, remember, 2300 or 3000, right? So it's way above. So what kind of flow you are? Turbulent? right? Turbulent. Okay, so we are dealing with the turbulent. So you see, whenever you have this thing, you can write it this way, DCR. Now remember, this one is critical, right? And you put it in the assumptions as well. Okay, so now you can say it's a turbulent flow. So for turbulent flow, now this time I won't be showing you the equation from the equation manual, because last class is all about the theory and showing the equations from equation manual. So I'll be writing that equation from last class, okay? So please try to coordinate with last class lecture here. And by the way, equation manual is uploaded in the Brightspace for you, okay? So you can print it and see it from there. Now I showed you two different kinds of equation. One with the friction factor, another one doesn't have friction factor. So which one you would like to use? Most likely not with the friction factor, right? Remember? So I was going to use the friction factor one anyway. So I can give you a quick review of the Moody chart. Okay. Any question up to this point? No? Everything's good? Isaac, you understand? Perfect. So the equation is F by 8. This again, I'm getting it from the equation manual. RED minus 1000 multiplied by Prandtl number 1 plus 12.7 F by 8 half square Prandtl by 2 by 3 minus 1. You see that? Okay, perfect. So now you'd be plugging the values. Now Reynolds and Prandtl, you know it, but the F or friction factor is the problem. So how are we going to find it? I'm going to use a different color, and I'm going to give you a little bit of demo here as like side notes, right? Which I did cover in last class as well. I don't know if you recall. So like you have this Moody chart here, right? On the Moody chart, usually you have in the x-axis Reynolds number. In the y-axis, you have the friction factor. In the y-axis right side, you have this E by D value. And that one, they call this thing relative roughness. Now again, this is done based on the assumption that you took the fluid class. If you don't took the fluid class, it would be difficult for you to understand, right? This is not like something in heat transfer class I'm teaching, because this itself, the Moody chart, will going to take few weeks for you to understand, right? You know that, right? Those who took fluid. And then you have a bunch of lines over there, obviously. I'm going to draw those lines based on the value of the E. I did explain this thing again in last class. So what you'd be doing, say like your E value is here in this slide, and you'd be finding the F value this way, right? The F value you'd be finding. So from Moody chart, I'll be giving you the value here. So from Moody chart, this is they call Moody chart, right? For Reynolds number and E by D value. Now E by D is, by the way, that relative roughness. The D is the diameter. What is the diameter here, by the way? Oh, we have a square duct. We don't have a diameter. How are we going to find it? You guys remember the hydraulic diameter? Anybody remember that from fluid class again? It's from fluid class. The hydraulic diameter you're going to find. So what is hydraulic diameter? Hydraulic diameter, I'm going to give you the equation. So diameter equation for this case would be DH, which is 4 AC divided by P. What is AC here? The cross-sectional area, right? So 4 multiplied A square divided by 4A. Do you see? This everything is going to cancel out. The hydraulic diameter is one side of the length of the square duct, right? So anyway, and the E value is the roughness value, right? You're going to find it based on the material, right? If it's aluminum duct, then the E for aluminum you're going to find it, right? They have the chart in the book, in fluid book. Okay. Anyway, once you're going to use all those things, okay, you'd be finding the value of F is 0.042. Now, here's one thing to highlight. This value of F doesn't have any unit because it's friction factor. Okay. Everyone's got it so far? It's a dimensionless number, F, friction factor. So once you have that, then I'll just simply finish the math. So I have on the math side, this F value is 0.042 divided by 8. The Reynolds is 32,610 minus 1,000. The Prandtl is 0.718, right? And then I have this 1 plus 12.7. Sorry about that. So this 12.7 multiplied by 0.042 divided by 8, 0.7166 2 to the power 3 minus 1, and the whole thing will gonna be multiplied by the hydraulic diameter, right? So if you're gonna I don't think there is a hydraulic diameter here. If you're gonna do the math, you're gonna come up with a value of Nusselt number 28.32 watt per meter square Kelvin. Tell me something, why I put a line on the top of that Nusselt number? As the average Nusselt number, remember? Because I'm interested to find the average age, so I'm interested to find how much of the total heat transfer happened from the duct to the attic, right? Everybody got it so far? With me? Perfect. So then, can you find the value of the age? Oh, by the way, this Nusselt number value is not that, by the way. I would be writing that that's the age value. So I would be writing that. So you have this age bar dh divided by k, right? So basically, I can move this k here, right? And I can move this dh here. You understand this, right? So I can only write h here. Hydraulic diameter is only one of the length a, just a. Okay, it's there's equation 4ac. AC is the cross sectional area divided by p, the perimeter. So perimeter is 4a, right? Because 4 side 1a perimeter, right? 4a, and AC is cross sectional area a square. If you do the math, you'll be finding the value. You see on the right side over there. I know it's distorted and everything, but when you end of the class, did you see that? That's the equation for hydraulic diameter. You got it? Differ? I'm sorry, this thing sucks. It's not me, it's this projector, okay? But here's the thing, I'm recording this video so you can watch it later if you have any question, any issues later, right? And I'll upload it, okay? So this h value is like that, right? Now obviously the k and dh value you already have, right? So the dh is the hydraulic diameter. This is the hydraulic diameter, okay? So then can you find the value of the q? Yes, it is very obvious. You just have this h a del t. Now look at here, what did I put as a subscript for del t? What did I put? Lm. Anybody heard about this Lm, logarithmic mean temperature? Anybody heard about it, logarithmic mean temperature? Matt, you heard about it, logarithmic mean temperature before? Log mean temperature, log mean, LMTD. They call LMTD, LMTD. Always you're gonna hear in heat transfer world all the time they say LMTD, LMTD. LMTD means logarithmic mean temperature difference. LMTD. Why do you care about that? Why do you need it? Because to find the Q here, you see, we are talking about a duct. Everybody look at here. Say like the duct running from here to the end of the class, right? All right. We are interested to find the Q of what? That the duct is losing the whole duct from here to the end, right? In the attic, right? So now this temperature difference, which temperature difference are you going to find? Because the temperature varies all the way, right? At the entering temperature is 85. The surface temperature is what? 75. Now, if the air goes like somewhere in the middle, the temperature is no longer 85. The temperature could be 80 or something different. So see, the change of temperature at the inlet of the duct, middle somewhere, at the exit, everywhere is different. Now, how are you going to do that? You're going to do some kind of average? Yes, but that average needs to be at every cross section in the duct, right? That's why you have to use this equation called logarithmic mean temperature difference. They call LMTD. Do you understand this? LMTD. This problem has so many aspects of it. That's why I'm just keeping this one single problem for this class. Okay, you don't want to take that much. All right. So then I'm going to write this logarithmic mean temperature difference. So LMTD. Let me write that thing. So log mean temperature difference. I did some shortcut, right? This logarithmic mean temperature difference, LMTD, is same as del T LM, is same as, now I'm going to give you an equation. Del T0 del Ti divided by ln of natural log del T0 del Ti. Now, does your common sense tells you what could be del T0 and del Ti? Del T, del means the change of temperature, right? Del T0 means what? The duct surface temperature, and the entering, or O0 means the exit temperature, right? And del Ti would be duct surface temperature, and the difference between the duct surface temperature and the entrance temperature. Everybody understand this? Your common sense tells you that. So basically, no matter how scary that looks, it's not that difficult to explode though, right? So you are writing this del MTD, where this del TO is Ts minus TO, del Ti means Ts minus Ti, right? Now we know what is TO, we know what is Ti, we know what is Ts. In the givens and the sketch we put it, right, everybody? Probably we put Te, but it's the same as To, right? Exit or O, outlet, whatever we want to say. Okay, let me check if I'm going to put Te or To. I put E, you change it to O. There won't be any confusion then, right? All right, so far, if you're going to find that, so what's our goal again? Our goal again is to find that del MTD, okay? So these two values would be, let me do the quick math. So our goal is to find this del MTD. Now, we can put it as equation number 1. Take a look on this equation. Do you know the exit temperature? This is one of the findings that you're going to do. It's a problem. We can't find del M, right? We can find del TLM or LMTD, logarithmic mean temperature. So we're going to find that exit temperature. There's an equation for exit temperature. In the equation, I know the equation is there. I'll be writing the equation now. Okay? Everybody? What is that equation? That equation is find T0, right? So Ts minus T0 divided by Ts minus Ti exponential minus PL H bar M dot Cp. Unlike external flow, the internal flow sometimes is a little tricky, okay? Everybody's seen that. Like, this is one of the most challenging problem out there. You won't be seeing that much challenging problem, okay? So I'm solving the most challenging problem ever possible. And then obviously you gotta start plugging the values, right? You know pretty much everything. So you have this one 70, this one T0, you don't know, this one 70, this one 85, right? Equal exponential. You have negative here, minus 4a, right? I talked about the perimeter already. P is the perimeter. So I don't want to go through the same route, which is 4 times 1 of the length of the square duct. And then this L length of the duct is 10 meter, then 28.32 watt per meter square Kelvin. The H value we just found. The m dot is, you remember, is the mass flow rate, which is the multiplication of rho 1.015 kg meter cube multiplied 0.1 meter cube per second, right? 0.1 is the volumetric flow rate and the other one is the density. And then you have this Cp is the specific heat at constant pressure, which is 1007 joule per kg Kelvin. We have it in the properties at the beginning, right? And the whole thing, if you're going to do the math, you're going to come up. It does look so scary, but believe me, it is not that scary at all, because it's just a math, right? You just put it in the calculator, you would be finding a value of 0.19 here. And then if you're going to do the math further, which would be obviously minus T0 0.19 minus 15 degrees Celsius, you're multiplying it, and the T0 would become 70 plus 0.19 multiplied 15 degrees Celsius, which would be 72.85 degrees Celsius. That's one of the findings, right? You got it? Now that you have the QT0, at plenty of time, I'm feeling very good now. So now that you have the exit temperature, can you find the Q or amount of heat loss from the duct? Should be, because what is the equation for Q? What is the equation for Q, guys? It is HA del LMTD, right? Or del TLM. You guys have the equation for LMTD? I did write it, right? Which is a combination of del T0, del Ti. You know what is del T0? Which would be Ts minus To, right? Remember that Ts is 75 given, right? And which is del Ti? Again, Ts minus Ti. So now that you have To, can you find LMTD? I want everybody to find LMTD. Once you have the value of the LMTD, you should be able to find the value of the Q. Now that I said LMTD probably more than 10 times, you know what is LMTD, right? What is LMTD? Log L. M means mean. T means temperature. D means difference. LMTD. Log means temperature difference. Can you find it? You have the equations, right? Everybody find the LMTD value. What is the value got? I'm talking about this. So you gotta find this del TLM, which is the same as LMTD, which is the same as del T0 minus del Ti divided by ln of del T0 divided by del Ti. Now, to find that, on the side note, you gotta find this del T0, del Ti, those are Ts minus T0, Ts minus Ti. Now that you have T0, you can able to find that. So the surface temperature is 70. That one would be 72.85 degrees Celsius. That one would be 85 degrees Celsius. And you're going to have a value of minus 2.85 degrees Celsius here and minus 15 degrees Celsius here. Then you're going to plug these values here. So minus 2.85 minus 15, right? And the whole thing is degrees Celsius here, and this thing will be ln of minus 2.85 minus 15 degrees Celsius. We're going to cancel out, negative cancel out. So if you're going to do the math, what is the LMTD value you found? Anyone? You know, found that value LMTD yet? Not yet? Is it negative 7.3? Is that the value you guys found? You found that. You find the value of the Q, amount of heat loss from the duct. You guys have the equation 1, right? Equation 1 was what? HAS del TLM. As you can understand, you have the del TLM now, right? Minus 7.3. What is AS? Is the surface area of the duct, which is the perimeter multiplied length. Perimeter is 4A, length is length, right? A and L is given. So it's just a math length. You find the value of the Q? Try. Everybody try finding the value of the Q. Everybody try to find the value of the Q, okay? So by the way, I did write it already, the equation. That is equation number 1. So you should be writing equation number 1 here. And this Q or heat loss, you have a different value? Not 7.3? All right, it could be. We're going to talk about it end of the class, okay? Because I am in a very tight schedule. After this, I'm going to jump into the radiation stuff, and then I'm going to show you the question, and then I'm going to talk with these individual things, okay? End of the class. Heat loss. Heat loss is like, H A S del T L M. Okay. So this H bar is 28.3 watt per meter square Kelvin. The AS is 4 multiplied 0.15 multiplied 10, right, meter square. And this LMTD is 7.3. You can say Kelvin, change of temperature, Kelvin or degree Celsius is the same. Kelvin, Kelvin, meter square, we're going to cancel out. And we'll have a value of minus 1240 watt. Can anybody tell me why I have a minus? What does it mean? What does the minus mean here? We're losing the heat, right? And the amount of heat loss, does it feel too big? It is not too big at all. So we are not losing for a 10-meter long duct, okay? So this sounds very reasonable, okay? You may don't want to buy a insulation for the duct, right? You may want to save that money. Every month, maybe you're paying a little bit more, but it's worth it. Does it make sense? How are you feeling with the problem? Pretty intensive, right? But don't worry, you are dealing with take-home exam, right? So you should be all right. If still you have questions and everything, let me know without hesitation. Now, I did upload a new homework. You would have seen that. I did say like I'm not gonna give it like I'm gonna give you the answers for that. Okay. So first of all, I'm gonna upload the solution manual for that new homework. You'll be seeing that new homework has a point of 2 or 3, I believe, out of 10. 2, right? So I only put 2. There is a reason behind that. All I want from you, I will upload the solution manual as I'm saying, right? So all I want from you, just after this class, I'm going to upload it. You review that solution manual. You try to solve it by yourself. And you submit it, okay? That way, and I'm keeping like minimum amount of points so it won't impact your grade, like only 2 points. Like if you prefer not to do that, okay? In case, who knows? So then it won't impact your grade, right? Only 2 points. So 2 benefits you can get out of it. First of all, you'll have exposure of more problems in internal flow that is going to help you with the exam, final exam, right? And I try to make it such a way you don't hamper your grade. Anyway, these are the small stuff. So to give you the overview of the problem, on this problem, we use the Nusselt number equation to find the H value, okay? That was something we discussed last class more than an hour. So without any confusion, you should be all right with the H, right? Okay, the problem that you are facing here, finding the exit temperature. Now see, I did use a new equation, right, for that, and that equation can be found from where? From the equation manual. Okay, you guys are busy with the project. I can assume next week, right? The presentation. It's all right. So, but watch the video lecture. Okay, so you see what I'm saying here. That exit temperature, that new sets of equation is also in the equation manual, which I did use. And the complete new concept, NIH, this is so important, this LMTD. Okay, you watch the video lecture, you see you spend more than 10 minutes on LMTD, right? So what is LMTD? It's log mean temperature difference. How will find it? What are the equations to use? All those things are here. Much more details here. I would encourage you to review one more time if you have time. Okay, I know at the end you guys are so busy with so many things. But if you have time, if you don't have time, it's still in summer sometime you will have the access. These are YouTube video, right? Watch it. Okay, try to understand. These are so important concepts. Okay, any question? Now I do have like I believe more than 15 minutes still, right? 17 minutes still. So these 17 minutes, what I'd like to do, I have a PowerPoint slides for revision. Okay, and as I said in the final exam, I have some subjective question, only one-line questions that I was asking, some of the parameters. By the way, those parameters I did cover at the beginning of the semester as well. Remember, I did cover some of the slides for radiation at the beginning. So I'll possibly do a little bit of quick review, and at the very end, at 12:15, I'm going to show you the exam. Okay. And by the way, the exam should be available to you now, and it's a take home again. I'm saying it's a take home due next week. Okay. No in class exam. Don't try to come here looking for me during the exam day. Okay. All I want you to submit it. Okay. In red space. Everything's good so far? Should I move on? As you can understand, this problem is a very lengthy problem. Okay. All right. So moving on to what I was just saying, the radiation stuff. This is the slide I'd like to emphasize. Some of the answer. Okay. You see that LMTT and everything, those are in the slides, by the way, uploaded all in Brightspace. Okay, everything is in the Brightspace. I don't know how much you explore on Brightspace, all the materials. There is module 8 over there, all these materials that I'm covering, everything is there. Okay, the equation manual including. Okay, anyway, these are the things that I covered. Obviously, I'd like to start my discussion from here, right, for radiation. Okay, so general consideration. Okay, let me go as much quick as I possible without hampering your understanding. Let's see how I can do that. So thermal radiation, okay, happen as long as same like convection and radiation, convection and convection, as long as there is a temperature difference. But the main difference between thermal radiation and other two things are thermal radiation doesn't require any medium. So how does this radiation happen from sun? How we are getting the energy? How we are getting the energy? Everybody know that, right? You heard about the spectrum, right? There is a solar spectrum, right? And solar spectrum, we are getting the what? Direct sunlight. So there's they call direct radiation, right? There's indirect radiation also. If you see, if you see something is glowing, you'll be feeling hot, right? Because of the glowing thing. This is direct radiation, right? What could be indirect radiation? Like now, today, if you go outside, meet, you feel warmer than nighttime if you go outside now. Yeah. Is there any sun you're seeing? There is zero sun today. It's cloudy, very cloudy. From morning till I didn't find any sun. There is sun. You are absolutely right, which is a trick question. There's sun is still there, right? But we're not seeing it. That's why we're feeling warm. But bottom line, we're not seeing the sun. That's not a direct radiation. That's indirect radiation. How is this happening? You see, there's cloud layer on the top of us. You know that, right? Because of the cloud layer, we're not seeing the sun. But if you're gonna fly on the airplane, pretty soon, after a few minutes, you'll be seeing immediately the sun when you cross the cloud layer, right? So the cloud gets warm, and eventually we are getting warm from the cloud, right? That's the indirect radiation. That's why during daytime we always feel warm compared to the nighttime. Nighttime there is no sun on the top. Okay, cloud or no cloud doesn't matter. We are not seeing anything, so nothing is contributing. But at nighttime still we are feeling warm. Why? Because during the whole day the sun did its job, warming up everything. So we are getting indirect radiation from that, right? Make sense? So that's the direct radiation, indirect radiation, and the radiation concept itself, right? And there are some questions here on the slides. I would encourage you to read through that, okay? Due to time limitation, I'm not going on that, because if I'm gonna start talking about that, then I'll be probably losing more time. Okay, here's the thing that I would like to really emphasize on that, which is the emission and the electromagnetic spectrum. Okay, how many of you seen this spectrum before? This is so important. How many of you seen this spectrum? All of you? Okay, on the spectrum itself, we are seeing here gamma ray, X-ray, ultraviolet, then thermal radiation or the visible light spectrum, right? And then we are seeing the infrared, and we are seeing the microwave. Now and then there is this other wave as well, like long wave, right? We don't want to talk about that, but let's talk a little bit about all those different spectrum that we're seeing here. Some of the spectrums we're very familiar with. Microwave. Pretty much everybody uses probably every day of that, right? The microwave radiation. Now, when I'm saying this different spectrum of the radiation, okay, the way it means is like, when you are in microwave radiation, I think you're familiar with the radiation spectrum? No? These are very interesting stuff I'm discussing, okay? The microwave would be a longer wave, right? As like you're seeing the wave, okay? Everybody see that? What I'm saying? Okay, if you want to go any back from the microwave, say like infrared, it would be a little bit smaller wave, right? You're gonna go further back, say like the visible spectrum, like blue, red, whatever we can see from our naked eye, right? So those are getting smaller and smaller. Okay, Isaac maybe I understand. So like you see, this would be like smaller like that. By the time you are coming to you see X-ray, gamma ray, and then the spectrum would be like the wavelength would be so small. It would be like jumping in a small space like so many times, right? So, so this is they call electromagnetic spectrum, right? So this is the whole spectrum that we're seeing here. But from sunlight, when I'm saying the visible light that we're seeing, the direct sunlight, we are getting only what portion? Only the visible spectrum. You understand? So that contribute to huge amount of radiation from sun. Excuse me. We are not getting the other, indirect portion like infrared is indirect. Everybody did the lab with the infrared, right? Infrared thermometer that I gave you guys. When you point out the infrared thermometer, okay, when it travels, did you see the infrared? No, it just give a point over there, but you don't see, right? Okay. So when infrared radiation happens, are you seeing it? Bottom line, no. Okay. So other than the visible spectrum, nothing that you can see, but still you can feel warm. Okay. Infrared is one of the major source to make something warm. You understand so far? Okay. The spectrum is so important. That's why I was trying to explain it to you guys. Okay. And then there is another spectrum here, right? The amount of okay, so there is this another spectrum here. Okay, spectrum. Monochromatic radiation emission, wavelength, spectral distribution, like so many things, new term that you're seeing here. First of all, anytime you're seeing the monochromatic, that monochromatic means only the wavelength, only you are dealing with only one specific color, okay? And then spectral distribution here referring to, in that case, like what is the wavelength that you are dealing here, and it could be varying all over the places depending on what is the source, okay? It could be from a man-made source, or it could be from anything that you're seeing around, okay? I don't want to go any further on that, but I'd like to move on this one. This one is so important. This one I did cover before. So let's go one by one. What is emissive power? What is irradiation? And what is radiosity? Okay, let's talk about those. So emissive power means, okay, think this way. When the sunlight comes, it warm up something, it is going to emit again, right? So that's the emissive power for that particular object that we're talking. Now, everybody, everything around you always emit the radiation based on its own temperature. Okay, say like I am standing here with a 98 degree Fahrenheit. This thing standing here with 70 degree Fahrenheit. So I'm emitting the radiation based on this 98 degree Fahrenheit. This surface is emitting radiation based on this 70 degree Fahrenheit. Now nothing probably happened with the surface from me, but what if I have a big fire source here, right? If I'm gonna have a big fire source here, I'm burning something. After some time, you'll be feeling this surface is going to get warm, right? Even though there is no direct contact with the fire of this surface, but this is going to still get warm. So how the heat is going to transfer from here to there? You may argue it will gonna transfer by convection, because the fire warm up the air and air is going to warm up this thing, right? That is one form of that, but it is mostly radiation, because you guys know like the temperature of the fire. Anybody? It's huge. It could be more than 1,000 degrees Celsius, depending on the fire itself we're talking, or the object that is on fire, depending on that. It varies all the way, but it is a huge temperature. Now, one thing that you already understand, when you have a big temperature difference, radiation comes into play, right? It makes sense? That's one of the reasons during winter, I mean up in North Country, everybody feels that, right? You turn on the stove, you turn on the fireplace, right? And you feel much, much warmer, right? Even if you are in certain distance. But that heat is not coming by convection only. Convection has part of it, because the air get warm up, but it's mostly radiation. Make sense? Okay, now another thing, say, man, you have a fireplace in the living space, right? And you have a bedroom just a little bit far from the living space, right? But not too far. But you, from the bedroom, you can't see the fireplace directly. Do you feel that you're gonna feel same kind of warmness from the bedroom? No, because the bedroom, if you can't see the fireplace, you can't feel warm. So that's the condition of the radiation. Everyone understand? The condition of the radiation, You need to see. That fire needs to see you, you need to see the fire. Then only the radiation exchange happens. That's then only the radiation exchange. Now you may say, if I have the fireplace open, fireplace turned on, even if I'm in the bedroom, I'm gonna feel still warm. Why? You have to understand that fireplace not directly giving you the heat, but it is warming up the surroundings, and you are indirectly getting the heat. Does it make sense? The whole house, but you everybody expose this thing, right? If you have a campfire, if you have a fireplace on, every time everybody wants to go as near as possible where the thing is glowing, right? And you feel much better just because of that. You have a direct eyesight with the fire to you, to fire. Everyone understand this? So that thing, whatever I try to explain here, these things are here. This thing they call view factor. Everybody see that view factor? So the source, okay, needs to see the sink. If they can see it based on how much of the angle they have, okay, the source and sink will exchange the radiation differently, completely differently. And this view factor concept, all those equations, complex equation and everything, you don't have to deal with any of this. If anyone interested, please let me know during the summer or whatever time. I'll talk more about it. Okay. View factor. View factor means things needs to be viewed by each other. Okay. And depending on the structure, the view factor changes everything. I haven't uploaded this thing yet. Sorry. Module 8 only, because I felt like, okay, I was going to cover 10-15 minutes only. But I was going to upload two things I'm going to do. The solution manual of the last homework 9, and this material, this slides that you're seeing here, the radiation slide, I'm going to upload it. Okay? Huh? Huh? Electronic. Yeah. Electronically. All right, what is the time? I guess this is the time. I can talk just a little bit with these things that you're seeing here, right? And then I'm gonna show you the question, okay? All right. So the emissive power. Everybody understand the emissive power, right? Everything will gonna emit, and this is the equation for that. Isaac, you remember the sigma? What is sigma? From first few weeks, sigma is called Stephen Boltzmann constant, right? Matt, you remember the epsilon? What is epsilon? Emissivity, right? The value would be ranging from anywhere from 0 to 1. All right. So then irradiation. Okay, let's talk about the irradiation radiosity. Okay, irradiation means the rate of radiation incident upon per surface area. So this sketch will gonna give you better understanding. The irradiation is saying how much of the radiation that you are getting on the surface, right? As if like from the sun, continuous radiation coming. Okay, and why you see the wiggle line and then you have the radiation? Because it usually comes as electromagnetic wave, right? Understand? Okay, so this wave is coming here as the irradiation, and radiation from that surface or the radiosity. Let me try to make it a little bigger. So the radiation on this surface, what happened when the irradiation come? Some amount will gonna reflected, some amount will gonna absorb, some amount will gonna get transmitted. Okay. Now here's the thing that I'd like to highlight. See, tell me if the sunlight comes here on the top. Okay, are you expecting it is gonna penetrate and come through the bottom? Okay, if you try to go under, you'll see dark, right? So that can't penetrate. So there is no transmission. See, out of these three components, transmission is 0 in that case, right? Why transmission is important? As if like you're dealing with a glass, right? In glass, you see the sunlight goes through, right? In the window, you can see outside. So transmission is there. Make sense? As you can understand? Yeah. So what happens, you see, think about this way, right? Even it's a cloudy day, in up here North country, everybody has the sunroof. Like this is very common. Why do you have sunroof? You like to get as much of radiation as you can, right? By the transmission. I do have sunroof in my house as well. Okay. So the next thing is the reflection. Reflection is very straightforward. If the radiation comes, it's going to bounce back some portion, and some is going to get absorbed. Okay. So that is like the irradiation, reflection, absorption, and transmission. Okay. Now here's the radiosity concept. Let's talk about that. You guys remember the reflection, right? One part is reflection. Now, there's the emission as well. Everything we're going to emit. I started the discussion with radiation with the emission. Remember that? I emit, her emit, this surface emit, everything emits, always, right? As long as it doesn't have some temperature. What is the equation? Everybody remember? Epsilon sigma t to the power 4. Okay? So that emission we're going to join with the reflection, right? And that is your radiosity. That's a new term that I'm introducing. Okay? I think that's enough. Now I give you at least something with the radiation, okay? Now, what will be happening here? I will be showing you the question, by the way, right? The final. What will be happening here after this class? I'm going to go to my office. I'm going to upload two things. One is the solution memo, and another is this material, the radiation material, okay? And let me show you the question. Don't go yet, please. Just one more second. I know I go a little bit more than expected, but just this is the last class. Last thing is already 12, 15. Just hang in there for a minute, okay? Minute or two. Let me quickly show you the question, the final question. So if you're gonna go content, and then if you're gonna go here to the final exam, right? And is it available to you already? Yes. Okay. And you see the due date is May 5th. It does says the due date, right? Okay, so there are these three questions. As you can see, the total points is 50, right? You see that? So see, the last question is radiation theory, based on the radiation theory that I was talking, right? So let's see if I covered everything. Did I cover the radiosity? Did I cover the emissivity? Did I cover the view factor? Remember the view factor I was talking? Radiation will only happen if one can see other, right? Did I cover the irradiation? I did cover the irradiation, right? Did I cover the transmissivity, absorptivity? Did I cover the diffuse radiation? Remember, I was talking about the indirect radiation. That's the diffuse radiation, right? Direct, indirect. I was talking about the infrared radiation. Did I cover the blackbody radiation? No, not really. That's the only thing I didn't cover. The blackbody radiation is very straightforward concept, as if like the surface, if the surface like this surface is so black, right? We'll be expecting the highest amount of emission, because what is the equation for emissivity? So what is the equation for emission? Epsilon sigma t to the power 4. This surface temperature t to the power t, whatever t. The sigma is constant, Stephen Boltzmann constant, right? The emissivity epsilon, that value can vary anywhere from 0 to 1. More the black the surface is, more the emissivity value is. That's why during summer, in hot summer, not in North Country, like if you're gonna go Florida or up in South or whatever, and you don't want to wear anything black, right? If you wear anything black, you'll be feeling so warm. That's why if you're gonna go Middle East, right, they wear too much warm during daytime, you'll be seeing pretty much everybody's wearing warm clothes, long warm clothes. They're trying to cover themselves, right, as much as possible. Okay? So the reflection is so much from the white cloth that you won't be feeling hot inside, right? Does it make sense? So that's the blackbody radiation constants come from there. The other example I can give you, right, when you would like to get the roof shingle, or the paint outside, you would like to go as light as possible. Up here in North Carolina, it's different story again, because we don't care, we don't get that much out of it, right? Only AC air conditioning require 1 week max, 1 or 2 weeks, right, in a year. But if you want to go south, right, if you have a darker color, right, then you'll be gaining too much heat. You'll be spending more money on HVAC. Anybody ever seen a picture of Greece? I don't want you to say like you went there, but anybody seen a picture of Greece? What are the colors of the Greece house? You'll be seeing all white everywhere, right? So that's the goal over there, to keep things cool, right? It's so warm over there. You understand? Anyway, so the blackbody radiation comes from there. Emissivity value is like as if like it's value of 1. So they did the experiment, right, long ago, and they made a shell like that where they have a tiny hole and they try to mimic the perfect black body. Okay, so that they can get the emission maximum amount of possible. Okay, so the ideas came from there. And there are 2 more questions. You want me to talk a little bit, because this is your final. This is optional. You can go. I don't really. But this is final. Your thing. You will gonna deal with that, right? So these both questions that you are seeing here, these both questions are internal flow questions, okay? So how are we going to solve it again? The two problems that we did, the homework that I uploaded, the solution manual of the homework that I'll upload now, okay, should be helpful to you, okay? Any question? I know I kind of rushed the last exam materials. I really don't any other way, any other semester, every semester I face the same issue. But hopefully I kind of started it such a way like 50 points and minimum amount of questions, take home, all the measures that I try to take, so you will not feel overwhelmed for the last exam, okay? It's good? Alright.
Just wanted to apologize for
I think you're good?
Yeah, I had a question.
Yes.
Well, I was just wondering if you're still accepting stuff until Tuesday under the finance. Specifically, project is another company behind it.
Remind me.
They offer you 28 6 hours more. It's okay if I'd like late points. I just want to make sure I'd still be able to.
Yeah.
True, I think that. It's an hour, the biggest thing that's an hour. But I won't, I sound like. Yeah, and the next one's gonna be $3,000.
Okay.
Yeah, and that one's